My name is Delilah.
And my name's Kenny.
Today, we're going to be explaining our Semester 1 Physics Capstone video. The question we're trying to answer today is, could I shoot a basketball into a hoop from a moving car that's going 10 miles per hour?
When she shoots the basketball, she's going to cancel the velocity that's created from the car on the ball. Meaning when she shoots it, she's going to shoot it at a very weird angle, and it's going to go into the basketball hoop with a very nice and beautiful looking arc.
Okay, and without further ado, let's get into the physics of this. To explain our experiment further, let's talk about restrictions we've set on the shot.
There are about a million different ways that we can shoot a basketball into a hoop from a moving car, so these restrictions will make it easier for us to figure out one correct answer for this problem. First off, when Delilah throws the ball into the hoop, she's going to be canceling the velocity created from the car onto the ball. That means when she throws it, it's not going to go forward in the same direction as the car, it'll stay in place on that axis.
Next, the car will be moving at a constant speed of 10 miles per hour, or about 4.47 meters per second.
The third restriction will be the basketball will be released at the same height as the hoop for the sake of ease of calculations.
Fourth, the hoop will be 2 meters away from the basketball upon its release.
Fifth, the ball will be in the air for 2 seconds before going in the hoop.
Before we go into the mathematical joy of this experiment, our last and final restriction is that the push will take 1/2 of a second.
In order to understand the physics of this problem, we must first understand the axes of this problem. This is a three-dimensional equation, and I've set each positive direction to be the direction of force Delilah will need to exert on the ball to get it in the hoop. Because this is a three-dimensional equation, and we've not learned about 3D problems in class yet, I've decided to break this up into 3 representations of 2D motion. This includes the XY, YZ, and XZ planes, each with 2 different axes. This means I'll need to analyze 3 free body force diagrams and an X, a Y, and a Z equation to fully understand the motion. The first axis we will discover is the XY axis, or the 2D plane with the X and Y axes. As you can see in the XY axis drawing, Delilah will need to throw the ball against the car's movement and upward, so this is what the free body force diagram should look like. The 2 forces acting on the ball are the normal force exerted by Delilah and the force of gravity. The velocity arrow is pointing up because the movement in the X direction is cancelled as stated earlier. The acceleration arrow is pointing up and left because it's accelerating against the car's movement while also accelerating upward. The second axis I'm going to cover will be the YZ axis. The new information shown by this graph tells us that we must obviously throw the ball towards the hoop. This is the free body force diagram for this axis. The new component of force, FNZ, indicates that we are throwing the ball toward the hoop, as discussed earlier. The velocity and acceleration arrows both point up and right to reflect the arc that the ball is going to make after Delilah releases it. The third and final axis I'm going to cover is going to be the XZ axis. This looks at the shot from a bird's eye view, or if you really want it to be, from underneath the ground. This is the free body force diagram for the XZ axis. There's no new force components, but the velocity arrow points right to indicate the ball going straight into the hoop, and the acceleration arrow points up and right to indicate accelerating towards the hoop and against the car's motion.
Now, we can solve for the force I need to exert on the ball to get it into the hoop. We first weighed the ball on a kitchen scale, and it read 595 grams. The next step is to convert the ball's mass into kilograms. After that, we use the free body force diagrams mentioned earlier to create equations for the X, Y, and Z axes. Since every axis is unbalanced, we set the net force equal to mass times acceleration, and with the mass of the ball found, we can substitute those values into each equation. Since acceleration is equal to change in velocity over change in time, we can substitute that into each equation, and since the push will take 1/2 a second, we can substitute that into time. The first force component we will solve for is the force component going against the car's motion, or the X component. Since we are canceling the velocity created by the car on the ball, we are throwing it against the car's movement with the same magnitude at a velocity of 4.47 meters per second. After substituting this value into the X equation and multiplying all values, we get 5.319 kilograms times meters per second squared, or 5.319 newtons. This value is how hard we must shoot the ball in the X direction, or the direction against the car's motion. Now, we are going to solve for the component in the direction of the hoop, or the Z axis. We are solving for initial velocity, and our givens are change in position, time, and acceleration, which is 0 meters per second squared because of a lack of forces on the ball after the push, assuming no air resistance.
The kinematic equation we can use for this problem states that change in position equals initial velocity times time, plus 1/2 of acceleration times time squared. Since I chose nice numbers earlier with the restriction, substituting all values and solving for initial velocity yields exactly 1 meter per second. Now I'm going to steal the z-axis equation from earlier and plug in the initial velocity that we needed. With this value, we can now multiply everything out to get a z-axis component of 1.19 newtons. Now let's solve for the angle that Delilah needs to make against the car's motion. Since we have the x and z components, we can use the inverse tangent function to find the angle that the force components make, which is 77.39 degrees. This is because the free body force diagram and the components in it create a right triangle that allow sine, cosine, and tangent functions to be used. Because of the fact that this creates a right triangle, we can use the Pythagorean theorem to find that the force needed in the xz direction, or the x-axis and the z-axis combined, is 5.45 newtons. We'll come back to this unit later. The last axis we will solve for is the y-axis, or the axis facing up in the air. Since the ball makes an arc up and down, the final velocity is equal in magnitude and opposite in direction to the initial velocity, and the change of position is 0 meters. We're also given time and acceleration, which is 9.8 meters per second squared due to gravity. Since we're solving for initial velocity, the kinematic equation, final velocity equals acceleration times time plus initial velocity works to find initial velocity. By plugging in all givens and solving for initial velocity, we get exactly 9.8 meters per second squared, which is no coincidence because the ball spends exactly 1 second going up and 1 second going down under gravitational acceleration.
Now, we can plug in initial velocity into the y-axis equation. By multiplying all values, we can find the net force, which is 11.662 newtons. To solve for the y component, we must solve for the force of gravity, which is equal to the ball's mass times gravitational acceleration. With these values, we can add the force of gravity to net force to get the y component force, 17.493 newtons. As shown earlier, force components make a right triangle, and as a result, we can use trig functions to find the angle made between them. Again, the inverse tangent function can be used to show that I need to throw the ball at 72.7 degrees facing upward. Additionally, this right triangle allows use of the Pythagorean theorem, which can be used to show that the normal force I need to exert to get the ball into the hoop is 18.32 newtons. In summary, in order to get the basketball into the hoop from a moving vehicle, I need to face 77.39 degrees opposite the car's direction and 72.7 degrees upwards. In this direction, I need to use 18.32 newtons of force over a half-second push. Now, let's shoot the basketball into the hoop.
This didn't work the first time for a few reasons. First, there are other external forces such as air resistance and wind that were not taken into account due to being too complex to solve for. Second, there's human error such as Delilah throwing at an incorrect angle that causes the ball to go off course. Third, and finally, how the hell do you throw a ball with 18.32 newtons? However, if we keep going, eventually Delilah will throw well enough that the ball travels at the right angle and force. That being said, we continue until the margin of error was small enough that the ball did go in, and we got this lovely video. Alright, so I'm almost ready for the final test. Say hi.
Hi.
I'm just about to start driving. Let's see how this goes. You ready?
We would like to thank Jude Nguyen for letting us go to his house and perform the experiment, and also for dealing with our antics. We would also like to thank Mr. Lesher for teaching us the fun physics involved in this video. Lastly, thank you, the viewer, for sticking with our physics today. See you next semester!